So welcome to the first lecture on vehicle motion planning, path planning for vehicles. And this will be introducing the attractor dynamics approach that builds on the idea of attractors, repellers, bifurcations, and so on. This would be a very good way to practice the dynamical system skills that we looked at last week. So I'll have to introduce the following ideas. I'll talk briefly about variables. We call them behavioral variables. Those will be the variables in terms of which we plan paths and motion. I'll talk about how time courses for those variables are generated from dynamic systems. They will be generated as attractor states. I'll talk about how tracking these attractors as they move generates complex behavior. And I'll talk about how flexibility arises from bifurcations where these attractors switch to repellers or disappear and so on. So that will be pretty much the first half of this lecture. And then I'll show an applied example in the second half. So this is my caricature of a robot vehicle. This little circle here is the vehicle. The red things are supposed to be sensors. I will not actually be talking about sensors in today's lectures. I will be just assuming that we have information about the world, and I'll characterize that at the end of the lecture as the symbolic approach. And next week, I will be talking about how to actually link the kind of path planning systems that we're talking about today to sensors, so low-level sensors. You see that leads to a slightly different interpretation of this approach. So this is a vehicle that's supposed to be able to rotate on the spot. You can imagine there would be like two wheels here. If in a real vehicle, I'll show you some actual physical vehicles later. So it's a system that can has 2 degrees of freedom. It has 2 wheels, let's say, and can turn on the spot. So it can, in a sense, determine its current heading, and it can determine its speed along that heading. It's not like a car, you know, a 4-wheeled vehicle with the complicated dynamics of steering and so on. It can reach any configuration in the world, in the 2D world, and a configuration in the 2D world has 3 variables. It has the 2-dimensional position, but also the orientation of the vehicle. So this is famous non-holonomic kind of system where you have fewer actuated degrees of freedom than configurational degrees of freedom you can achieve. And you can always think of that as reaching just some point in the plane and then rotating on the spot to have the orientation. So we'll not go very much into that. That's actually an issue that path planners in more, let's say, more detailed variants, where you might also take into account the shape of the vehicles on look at. We take this as a very simple exemplary case of behavioral planning. So when we're saying we want to plan a motion, what we really mean is that we want to create some signal that we could send to the motors of that vehicle and make these vehicles, the motors, create some action so that the vehicle does what this plan reflects, what we're planning for the system to do. And the variable in terms of which we're planning, that's the behavioral variable. And in all the examples we'll be looking at, that is the heading direction of the vehicle. That's a very general variable that turns out to be actually right to describe what humans do in situations like that. In the second half of today's lecture, I will actually be talking about human pedestrians, how they walk around in the plane. So just how their body is displaced in the plane. It's also as the steering angle, a variant of this, or a representation of this is the steering angle. That's one of the variables that autonomous vehicles, cars, control, the other being the speed, right, along the path. And you will later see in the second half of this course that in movements of hands, robot hands, or human hands in space, there's also a variable sort of like that, which is essentially the direction of the movement, the hand's movement in space, that plays a similar role. And those of you who saw my winter semester course, you might remember there's the population vectors or neural representation in motor cortex of movement plans, and that is about hand direction in space, and that's essentially a heading direction. So it might seem a little bit arbitrary variable, but it's actually a variable that captures something essential. So this is our first encounter with it. So I'll define it now. Over the course of the next two lectures, you will be seeing more interesting wrinkles of that, subtle wrinkles of it. So for now, what I'm talking about is a characterization of the heading of the vehicle that is relative to some fixed arbitrary world frame. So if the vehicle had a compass, we could say we measure the angle from north, let's say. And so that translates with the vehicle. It's always, from the point of view of the vehicle, the direction to this absolute north, and then an angle from that. So let's say this axis could be that. It turns out our vehicles don't need a compass, and typically don't have a compass, and there will be an arbitrary axis that is essentially defined by the initial state when you start the robot first, and you give its internal representation of heading direction some value, let's say 0. Then the axis relative to which this heading direction is defined is the direction which the vehicle is initially pointed. It will turn out it doesn't really matter if you keep track of that variable, and I'll be showing why. The only requirement is that your estimate of your current heading, which really means your estimate of where that world axis is, shouldn't become imprecise too quickly. It can become imprecise, and it doesn't matter if it's even totally off after some time. It doesn't matter, as you will see, as long as you have some sensory information about the world. But if it were to drift too fast, then there could be problems. So just a hint that there is some issue about that. So this is a good variable, and one reason why it's a good variable is because it allows us to express constraints on the path planning. So the two constraints we'll consider is target acquisition, that is moving in the direction of some desired object. Let's say this is a target object, and then the angle from this world axis to that object that will be the heading that is desired. That will be the heading that would take you to the target. This is what in the Navy is when you're talking about a heading, like you're driving somewhere. You're taking a ship somewhere, and you've computed from your current position a map in which direction relative to north a certain target lies. Then you're telling your actually I forgot the English term for that. Your pilot, which direct course to steer. This would be called the bearing in Navy language. In German, we say the Peilung, in the direction which the target lies. So, that's the target constraint, and then you could have obstacle constraints. That is, there are certain directions in which you don't want to move, at least not in the long run, and those would be angles relative to that world axis in which you find some physical structure that's not your target that you want to avoid. So psi-ops in heading direction terms. And with the obstacles, you would typically avoid a whole range, and I'll get into that a little bit later. Actually, next week I will get into how exactly you compute that range. If you have some idea about the size of the obstacle, you might have to add something on the left, on the right, so as to make sure that your vehicle wouldn't touch the obstacle if it were somewhere close there. So that's one feature of these variables, or you could say it's a good variable for planning behavior, in that it expresses constraints as values or ranges of values. It's also a variable that describes the desired motor behavior, in the sense that if you realize it, then a desired motor behavior arises. And realize it means if you make that the vehicle actually moves in that direction. I call this loosely enactable. Technically speaking, you would have to look at something like controllable, which I'm not going to define here. So it's maybe very intuitive that you can realize that, and to actually understand that you have to know a little bit about the control of the vehicle. And this is something I will not be going much into now, but we'll later in the course, we'll actually talk about how dynamical systems like that interact with control. We'll do that in the context of arms, not of vehicles. So enactable means that we're able to send signals to the motors, which will be some currents we send to the motors or voltages that create currents, so that the wheel turning of the vehicle makes that the heading of the vehicle approximates a desired heading. You will see later that it's really the rate of change of heading that is the command. And the rate of change of heading is realized simply by giving a different speed to the two motors. Right? If the two motors turn the same speed, you're going straight. If one of them turns faster than the other, you're turning, just like in the Breitenberg example I mentioned before. And in the, you need a model for that. So you need to know how large the wheels are and how far they are from each other to figure out exactly how much difference in turning corresponds to how much turning of the vehicle. And that can be figured out. And then the only remaining act of enacting a heading direction or a change of heading is that you are able to create desired turning rates of those motors. That's the issue of control. Because the motors will encounter resistance, the vehicle has inertia, and you might have even you could have slip. You know, there could be some problems with that. This is not 100% sure a priori. So to overcome inertia and physical forces, you need an actual control. You might have a servo motor, for instance. The examples I'll show you have servo motors, so that they correct for any resistance to the turning. If there is slip, then you actually make a mistake. You don't really approximate the plan. And what will happen is that your plan will be updated. We'll come to that. The more subtle point about this is that it has the appropriate level of invariance. Roughly speaking, that means that when you're in a situation like this, you have the target here and the obstacle. It doesn't matter how your vehicle is initially oriented for what these variables, these values are. If you rotate, the green thing is supposed to be the forward direction, the nose of the vehicle, the wheels would be on the side. So if you were to rotate the vehicle on the spot, then this angle, which is the heading of the vehicle itself, would vary, but these angles relative to the obstacle and the target, the bearings, would be unchanged because they're measured relative to that fixed world axis. If you were to measure these angles in terms of body coordinates, so from this green line, then these angles would change when the vehicle changes on the spot, and that actually makes it harder to control them. That is the picture that is often used in control theory, where you just have one variable like that, and where typically you want to make that variable zero. I mean, that variable is called an error and make it zero. For instance, if you want to steer toward the target, you would take this angle between your heading and the target, call that your steering error, and make that zero, and then you would be heading to the target. So that's measuring the constraints relative to the frame in which you're actually acting, relative to the heading of the vehicle. You can maybe immediately intuit that that's not good for integrating multiple constraints, like an obstacle constraint as well, because then these different variables interact, right? If you consider that the error, then there is some other variable that in the avoidance angle that depends on the error. So that all the constraints become interdependent. That's real annoyance. And so what we're actually postulating is that the constraints are invariant under the motor variable heading direction. And that's the case here. Good. Now, that's one idea. We have this variable. The next idea is that we will generate behavior by generating time forces of that variable. So on the actual robot, we'll have a computer that will run numerical software, and that software will be informed about targets and obstacles, and I'll gloss over how. And we will have that computer solve an equation. It will be a dynamical system that it solves numerically so that the solution generates a time course of these behaviors. And whenever you have a current heading or a current change of heading as a variable, you'll send it to the motors and realize it. And so that's the encoding of the plan in a dynamical system. That's a non-trivial idea. Other representations of that, for instance, in classical planning, would be really to have time courses represented as pieces of trajectory, as functions of a parameter, some kind of virtual time that you really store. And for instance, in a lot of path planning approaches, I'll review a few of those at the end of like in 3 weeks. In many of these approaches, the time course would be the solution of some kind of integral of a time that is optimized, finding the function that minimizes some cost function. And to do that on the computer, you represent the time course with some discrete sampling as a trajectory, and then send that trajectory down to your controllers as a desired trajectory. So here we're using this compression of a dynamical system that you actually only represent the instantaneous value of the variable, and the time course emerges as a solution of the dynamical system. And the dynamical system per se is here autonomous. It only depends on sensor inputs, but it's not like it needs to keep track of time. Time is implicit. And so what the dynamic system, so what we have to do to design the plan is to design the dynamical system. And we'll construct the dynamical system from a number of terms, or the equation, the right-hand side of the equation, from a number of terms that essentially express the behavior constraints. And the key idea for that is that we'll make the dynamic system have an attractor at desired values. We'll also postulate that there are repellers at undesired values. And by combining these different contributions, we'll make sure that these constraints are satisfied. So here's simplest example, just going for a target. That will be a dynamical system we'll have to erect that has an attractor at heading direction equals to that bearing angle of the target. So we'll call the heading direction phi, and what we want is phi equals psi, this angle to the target, being an attractor. And so the dynamical system will be a function in which the rate of change of heading is a function of heading, right? That's a dynamic system, remember? X dot as a function of X, here it's phi dot as a function of phi, where phi is heading. So if phi is heading, phi dot is the rate of change of heading. That's actually the angular velocity of the vehicle. It is the planned angular velocity, right? The vehicle still has to then do some control to actually achieve it. That's angular velocity in the plan. So for that to have an attractor at the desired heading, psi tar, the index tar belongs here, just means that we make sure there's a zero crossing here with negative slope. Remember? Negative slope, a fixed point with negative slope of the dynamics around it makes a local attractor. So again, as we went through last week extensively, if you're to have a larger heading, then you have a negative rate of change, you go left. If you have a smaller heading, you have a positive rate of change, you go right. In all the examples I will be taking, I'm cheating a little bit with the plots because mathematically we have this odd tradition that angles grow counterclockwise. So the angle becoming larger really means you turn left. So as you turn left, you move to the right in this plot. And that's very confusing. So when I compare with the graphs, I will just flip everything. And so going to the right also means turning right. And in all our implementations, just to be consistent with the mathematical notation, we always do it the other way around. Should normally not be a problem. In the lectures, it will be as in the more intuitive forms. In all the formulas in the papers, it's always in the opposite direction that phi is defined. Okay, so that's how you do an attractor. A repeller, well, it's just the same thing flipped, right? If I have a particular direction that I want to avoid, I make it a repeller so that if I'm a little bit to the right, I'm in here actually a little larger heading, I have a positive rate, so I increase my heading further, I'm moving away from that undesired heading, and the same on the other side, right? A little less than that, I decrease negative slope, decrease, negative function, decrease the heading. You could ask, perhaps, why would I have zero rate of change when I'm heading exactly for the obstacle? And that's a question we'll come back to. So you could say, well, if I'm, just to the right of this, I might want to have a very large rate of change to get away from it quickly, and then jump to a very negative rate of change when I'm just on the other side. So make it more a jump, not go through zero. That might sound seductive. It's a terrible idea, and you could imagine already intuit might be a dynamical system that no longer is smooth, so existence of uniqueness of solutions isn't guaranteed. And you might actually run into things like that, because you can sometimes actually come close to an obstacle because it's still far. We'll come to that. So that's not a good idea. And yes, we do actually really become slow as we ride at the obstacle. And in practice, we actually even add a little bit of noise to our equation, so that if there is an odd case where we would just be heading for that repeller, we really get away from it with a little bit of noise. It's never perfect zero, your rate of change. So with a little bit of noise, it would be either positive or negative, and then you would actually really start to move away from that. And you will see it actually does happen that you are sitting in something like that, a repeller, and it happens in a bifurcation when you previously had an attractor there, and then it becomes a repeller. And then you are sitting in the repeller and you have to get out of it. Okay. I'll talk about the range in a moment, and here's the characterization generally of these forcelets. So there are really three parameters that characterize these functions. We call these forcelets, these individual contributions, for the analogy with wavelet, in the sense that they have a finite range. And so the three parameters for them is where the zero crossing is. That's what I already talked about. How stable or attractive or repulsive they are, and that's the slope of this. We call this the strength. If a steep slope means a small deviation is counteracted strongly. In the repeller, analogously, you have a steep slope means that you're being pushed away from the attractor at the same distance quite strongly. The steeper the slope, the more strongly. And that shows up in the time scale. That's a very fast exponential growth away from the repeller, or here exponential attraction to the repeller. The third term is sort of a range function. And it's not here from peak to peak, because the peak doesn't matter. This is the turning rate, but I'm still having a negative turning rate here. So the range should more probably be defined in terms of some threshold rate of change when it goes to zero. And we'll use often Gaussians to modulate the size of these terms, and then it will be some measure of the width of the Gaussian, like 2/3 of the where the turning point of the Gaussian is. Some measure, it's just a measure of the range. So for the attractor forcelet, it's not so obvious that we want a range, because if you have an attractor like this, maybe even if you're heading in the exact opposite direction, would you still want to turn around and go to the target? So we'll not actually use the range particularly much. You see, these are dynamics now on the circle, because the dynamical variable is an angle. So the dynamics needs to be periodic, 2 pi or 360 degree, what kind of metric you use for the angles, periodic. Which means, I haven't drawn that very clearly, that on the back side, you will have another zero crossing, right? If you're negative at angles larger than the heading to the target, and your rate of change is positive for angles smaller than that angle, somewhere on the back, just in the opposite direction, that must change again. You must go from the negative to the positive, so another zero crossing. So very often we model these dynamics actually in terms of sinusoidal functions, sinus and cosine functions, so that they're periodic. If you did not do that, then there would be a jump somewhere in the back, right? Somewhere in the opposite direction, you would jump from, let's say, negative heading to positive heading. And again, jumps are always bad, because you could be forced to run sometimes in the opposite direction by obstacles, and then you would get unstable behavior at the jump. And the dynamics has no unique solution. So for the target, typically we use actually really sinus functions. It's technically speaking, if it's centered here, it's a minus sinus, right? The sinus would go up, minus sinus goes down. And that has, we would say, no special range. That it extends over the whole circle, the 360-degree circle. For the obstacle, we will typically use a real range limiting function, because we will think that we don't really want to be affected by the obstacle if it's behind us. And you have to decide as a designer how far that influence reaches. So for instance, here you might even say, well, even if I'm heading currently in this direction, I don't want to be affected by this anymore. And that would mean that you're making sure that the range of heading directions over which this acts is so small that it doesn't reach that level of phi that you're at. Let's say we're steering here at this level of phi. We want to make that range so that there is no influence of that obstacle at that level of phi. And that's what we will be controlling when we control the range. And so very often what we do is you will get examples for that from the papers that I'll give you. And there are already 2 papers uploaded that show that. We will multiply a linear function with a Gaussian, and that Gaussian can control the range. And the exercise I will be uploading has 2 parts. The first part is exactly you playing with that kind of formula to figure out how to control these 3 numbers. And it's very simple. You just plot the Gaussian and think about how the Gaussian affects the slope here and the drop-off rate and so on. Okay, so let's look at how we can then combine different constraints like that. And I'll take you through an academic example that's very clean, although that's not what we use in practice, namely having 2 targets and fusing these constraints. And then I'll talk about obstacles and targets, which is the more relevant constraint. So our idea here is that we add the contributions to the dynamics. It's sort of an ad hoc idea that doesn't actually guarantee yet by itself that all the constraints are going to be satisfied. And we'll see that. There can be new attractors that emerge that are not exactly the ones imposed initially. But we can work with that. And the more general solution will be to really numerically impose that the attractors and repellers are at certain values, which is something one can do in some simple cases. You will later see that the actual bottleneck is more sensory information about the targets and obstacles, and not so much how, in these so-called symbolic representations, how to make the optimal fusion. So here, if we had, so again, I call these things force-led, right? So, because they have a limited range in general over phi. That's just jargon. We invented that word. So here, you see, intuitively, there would be 2 kinds of cases. One case would be that the 2 directions in the 2 targets would be quite close to each other. Intuitively here, such that you would actually, you could even position the vehicle on top of these 2 obstacles. But that's a question, of course, of how far they are from the current position. So the angle that we're talking about. So if they're close, we want to fuse, we want to drive into an average direction of these 2 targets. These lila functions here, violet, reflect the contributions of the individual targets, and the red is the sum. And you see that sum has a fixed point that is at an average position between the 2 individual fixed points. It's also an attractor. And so the red curve has a single attractor. That's a fused attractor, so in the middle here. And that comes from the fact that these lines are pretty much parallel. So they're the slope is actually a steeper slope. You can't see that very much, but it's a bit steeper than the individual slopes. And it lies at these 2, somewhere in the middle. If the amplitudes of the 2 functions are slightly different, you could have targets that have different degree of actual attractiveness, for instance, then that would be a weighted average. So that's it's not actually maintaining the individual constraints, it's fusing them. Now you could think in the other extreme, if these targets are sufficiently far from each other, then they should be sort of independent of each other, and you could not realize both at the same time. You would select one of those to fulfill. And so for instance, if you're selecting this one, then you would be ignoring that one. And that would be automatically the case if you make the width of these force-led such that when one of those here is actually a lila curve underlying this red curve, and then that goes this way, right? So there is an attractor here that comes from one of those 2 contributions. And you see the red curve lies on top of the green because the other contribution, which is centered around this, is pretty much zero in this regime when it starts to turn up a little bit here. So they hardly overlap, and therefore they do not really interfere. And similarly here, the other contribution, has pretty much no contribution on this side. So the fixed point comes to lie where the fixed point of the individual contribution comes to lie. In between, the two contributions are both present and cancel each other. So you don't turn to the left with quite the same strength as in the individual case. And you have this repeller that kind of emerges here that acts as a boundary of the basins of attraction. The basins of attraction are the ranges of initial values from which you are attracted to a particular attractor. And so, this here is the boundary between these two basins of attraction. If you're heading anywhere below this, you will be attracted to this attractor. If you're heading anywhere above that, you will be attracted to this attractor. So if everything's symmetric, it will be an angle that is pretty much the average between these two. If you're to the right, you will be going to this target, to the left, go to that target. There is some kind of, you see that one target pushes in the opposite direction as the other target. So there is some kind of cancellation. And this can actually sometimes become problematic, that you are in an equilibrium between these two positions. I think I got a question here. What about if it's in the middle? Yeah, so if you're, for instance, driving exactly in the middle direction, you're sitting in a repeller, so that could be a problem. And the solution will be that it's an unstable state. So if you have a slight deviation from that repeller, for instance, because you're not perfectly in the middle, or because as you're driving, the angles change a little bit, one is closer than the other, or even just noise, sensor noise or motor noise or planning noise. We would actually, in our implementation, sometimes add explicitly noise that will make that you're not staying in the repeller exactly. And as soon as you're deviating from the repeller a little bit on the light on the left, you will actually go to the corresponding side, to one of those. So yes, you have to break that symmetry, get out of the repeller. That will be the answer. Of course, in general, it would be very odd for you to be sitting in that repeller, because how did you get there? So the only way there how you couldn't get there is that it arises out of a previous attractor, and that can actually happen. If you do something like this and make the contributions depend on distance, then you might not have had the repeller sitting there. Actually, we don't really do this for a target fusion, but you will see an example like that for repellers in a moment, for obstacle avoidance. So you could think of this as a bifurcation. First of all, this is a bistable dynamic system, so it makes decisions, right? And I think I mentioned that before. I'm not entirely sure. So just depending on your initial heading, you will be deciding for one or the other target. It's with your body that you decide, right? The body turns, the robot turns, and once it's turned, then it's only going to one attractor. This transition from averaging to decision making is a bifurcation. You could think of the angular opening between the two targets as a parameter that spans a family of dynamical systems, right? And that family of dynamical systems has a qualitative change from having a single attractor to having two attractors with a repeller in the middle. So here, this plot illustrates a bifurcation diagram. This would be the attractor, the angular heading direction where there's an attractor and a repeller, and as a function of increasing distance, the system would bifurcate from a single attractor when they're fused to these two attractors, one to the left and one to the right with a repeller in the middle. This would be actually a pitchfork bifurcation. And so this would be happening if the two targets are exactly symmetrical, same distance, same parameters, whatever parameters influence the strength of attraction. Then you could have that symmetric case that it really splits like that. Remember, I discussed last week, this is a codimension 1 bifurcation. So in addition to having to be at the instability, you also have to have a second parameter that makes sure that these three things collide at exactly the same point. That will be the symmetry. So if one of these attractors is more attractive than the other, then you will actually get an attractor to continuously just deform, and the other one will actually make a tangent bifurcation. So this repeller will collide with the one in the attractors and disappear that way. That's the unsymmetrical case, and that would be, we would just see that the option of going to one of those disappears at a certain, when the distance between the target decreases. So that's a bifurcation. That's a very general way that we'll see that the constraint satisfaction is resolved. So we're either fusing constraints, averaging essentially constraints, or we'll select constraints, and it will be bifurcations that tell us how we do that. So the more realistic case is, I'm saying this is not so realistic because usually you would select the target at the perceptual level. You might have some feature, where you can, the targets are objects and you select one object, you're not fusing them this way. You might do this more for obstacles, because actually obstacles, you're not so interested in them as objects, right? They're just some stuff you can collide with, and you might want to deal with it just at this behavioral level. So here I'm creating a situation which is really somewhat complex, where I have a target and two obstacles. And I'm suggesting this is a situation where you can avoid the obstacles and still go straight to the target as if there were no obstacles. You could just go straight through this opening, and the dotted line suggests the robot fits through there. So that would be a case, in other words, where all these constraints can be imposed independently of each other. They're not in conflict. And you see this here in the plot. This pink line would be the attractor to the target, would have a attractor here at this angle, which is supposed to be the angle to the target. The green points here mark attractors. And then you have these, I don't know, brown or orange curves that are two force-sets for repulsion. Again, using this trick, I'm saying this must be the left obstacle. It's actually the right one. So there's a repeller here, positive slope of this orange curve, right? And there's another one here for the other obstacle, positive slope. And the black line here is just the sum of these three curves. And you see that the zero crossings of the black line lie exactly on top of the zero crossings of the individual curves. So you have repellers here and an attractor here, exactly where they're supposed to be. So the constraints are not in conflict. It's sort of the reverse picture, right? These positive slopes are parallel, and the average curve is then a little bit steeper than these individual contributions. You notice that the slope for the target is weaker than the slope for the obstacles with the opposite sign, but it's weaker in absolute terms. And that's on design, on purpose. You could say the steepness is the strength of attraction. How much turning do you create when you are at the same distance from the fixed point? And general idea is that you always want to, the strength of the dynamic term in this terms of the slope reflect some kind of controlled priority or planning priority. That is, those things that you want to primarily, the constraints you want to primarily satisfy have to have steeper slope, and therefore they will be voting more strongly for their constraints than those that you find secondary. So the obstacle avoidance is always primary. You don't want to collide, even if you have to make a more roundabout way to the target. So you make the target contribution the weakest term. Weak means your flat curve. And that's why this flat curve doesn't really affect how the positive slopes combine here. You see the positive slopes here combine almost like the previously the attractors combined to a shared they are on the other part, right? This on the decreasing edge, they line up, make an attractor here, and that's not affected by the attractor from the pig diamond. It's somewhat, I mean, it's somewhat stabilized, but you could neglect that. There are two new attractors here on the outside. They are sort of emergent, and there's no special term that made them, and they come really from the fact that you have a force here that repels you from this obstacle. That's this positive turning rate, and you have another force that attracts you to this attractor, which is weaker, and so these two cancel at this point. and that makes an attractor. You can think of these obstacle terms as sort of half attractors, right? So you see, if you think of this zero crossing here, then it's half attractor. That is, if you have a smaller heading, you are driven to this point. If you have a larger heading, then this obstacle contribution, goes to zero, doesn't have an influence. It's only attractive on one side. And so it's this half attractor that combines with the attractor different position to create here another attractive situation. And the same on the other end. And so intuitively, these three attractors correspond to the three solutions that you could visualize here. One is going straight through. That would be the attractor dictated by the target acquisition term. And then you would have one, going around the whole obstacle here on this side, and you have another one going around the obstacle on that side. So these outer attractors are these solutions where you go around the configuration. This is the dynamics at one moment in time, at this moment in time. And at some later moment in time, the robot will have different heading bearings of these obstacles and targets. So these terms shift around. We'll get to that. We'll look at that. So I can only say that these outer solutions would lead to that path, but we'll have to then figure out how the dynamics actually evolves as the robot moves. So that's the case where the constraints are not in conflict. And if I now move the obstacles in, I create conflict intuitively. This would not be a path the robot can take. And what I want to do as the designer of this planning dynamics, I want to make the dynamics such that when that happens, you no longer have an attractor here in the middle. Instead, you have a repeller. So now I'm actually averaging the repelling side of the forces to create in the sum, a summed repeller, and that overpowers the attraction to this direction. And so there's only a repeller left here. There's still these outer attractors left. They are not really affected by that. So you can always go around it on the left, on the right. And that's actually generically what will happen. So if you're a little bit to the right of this repeller, you'll converge to the solution going around it on the right, a little bit to the left, going around the other way. And you recognize that this is actually also the same kind of bifurcation. It's actually the inverse. This is the subcritical if the other one was the supercritical bifurcation. So the bifurcation diagram here is now a function of increasing distance between obstacles. Previously it was distance between targets, and the repeller is now the outside stuff, right? There's a repeller here that splits into two and then a attractor in the middle. And previously it was the other way around. Remember I told you that all the bifurcations exist in super and subcritical form, as we call those. So one is time runs in one direction and the other is time runs in the inverse direction. So in one direction, this is an attractor, these are repellers. If I let time run backwards, the repellers become attractors and the attractor becomes a repeller. That would be the other bifurcation we just looked at. Well, these outer attractors are not going through any bifurcation. They're always there. And they would just deform a little bit. So again, this is a bifurcation. It's again symmetrical because we're assuming that the two obstacles with same strength and exactly same bearing and range, exactly symmetrical bearing, would be moving in. And that would be sort of the extreme limit case. And in next lecture, when we'll talk about sensory information, we'll see that that is actually generic, that you have to think about the symmetrical case. Because if it's asymmetric, it's much simpler. We'll see that in a moment. But that's sort of the most critical case when two things happen at the same time. So that's how you will be switching your behavior from attraction to repulsion. So you see that for understanding how this works, it's important that we just think about the attractors. We're using qualitative dynamics. That is, we're just thinking about the attractor, and we're making sure that the constraints are satisfied in the attractor, and we're relying on the attractive property to say, well, everything within the basin of attraction will fulfill the constraints. We'll just have to make sure that we are attracted fast enough. As the vehicle moves, things change a little bit. So if the attraction was arbitrarily fast, then we would make sure that the constraint is satisfied as long as it's satisfied by the attractor. And so the repellers are really just separating these different regimes. So that is a solution that's attractive because we don't need to design all the solutions I call those now transient here. So from any initial condition to satisfy all the constraints is enough to just design the invariant solution, the fixed points, and the attractors repellers to fulfill the constraints. And I will be presenting to you the so-called potential field approach. It's much more much older and actually still used a lot by a lot of people, which doesn't really make much sense, but because it's so well established, so easy, it's being used. And that's actually using this kind of logic for all transient solutions. Is one of harder to design right, and actually generally doesn't work. It often creates some conflict which you have to catch by some error handling. So this is a real advantage of this approach, that we only need to make sure that the attractors and repellers are right. And we can use, in a sense, bifurcation theory to erect the right dynamics. That is, we could just say, this is the diagram I want, and now I could use the normal form to write down an equation that is like that. Unfortunately, we don't do that on the robots because, again, the angle, this variable is an angle variable, so the normal form, which is polynomial, is not periodic. So instead, we use sine and cosine functions to do that. But it's sort of lifting that to periodic functions. So maybe the one point you might worry about, though, is, how is it possible to create a whole plan, so let's say complex time course of the vehicle moving, if it's just always sitting in an attractor, right? Wouldn't that just mean it can always just go straight? It's an attractor. And it's a good question. It needs to be studied. The reason is essentially that you're moving around, that we use a velocity type variable. Heading direction is the angular aspect of velocity, and when you're moving, the heading direction is your instantaneous direction of your path velocity. And you can be sitting in a constant velocity and still have some fun, right? That's what you do on the highway when you drive. Maybe you have a speed that's constant. You actually do change your steering, and you're having fun. Let's say, in a sense, something interesting happening because you're moving through the world, and as you're moving through the world, constraints change, targets and obstacles change, and therefore your dynamics change, and therefore your attractor moves, and you're moving with that attractor. And I'm trying to illustrate that idea here. Here again, I'm using that trick to, this is actually where I really flip the plots to make it more intuitive. And in the original paper where this is from, you see it's one of those is mirrored. So here's the target. Here's the obstacle. You have an initial position like that, let's say. And so I'm using the same color code, that is the lila or violet term is the attraction to the target. So you see the target is a little bit to the right of the robot's initial heading. The robot is sitting here in this attractor. The green is the sum here. Unfortunately, I took green here rather than black. So this is sitting here in this attractor. And you see it's a little bit to the right of that is a repeller, which is this obstacle here, and of the individual contributions. And here would be the target. And the sum, again, is the green. So the sum, you see, actually does have two attractors. There is the one you're sitting in, going here. And then there is the one on the far right, which would correspond to going around the whole thing on the right. And that's the solution we're not taking currently because we're heading in this direction. There's also a repeller here, which lies sort of in the opposite direction. So somewhere, in this direction, you decide between trying to reach the target on this side versus trying to reach it on the other side. So you will be switching your strategy if you're moving away from the obstacle in that direction. So that's at that particular moment in time, right? So you would be sitting here, and as you're sitting there, you're driving. The speed with which the vehicle drives is another control variable, another behavior variable that in some of the models that we're using, we actually also design with the dynamics. I'm just not talking about it now. I might give you a paper later to read where you can study that. Essentially, you just want to drive slowly enough if you're close to collision so that you can really track the attractors. Other than that, you could just drive at constant speed. So because of that speed, at some moment later, you will be in a new position. For instance, let's say in this position. This is taken from actual simulation. And when you're in this new position, you see that the bearing angles have changed, right? Now your target is actually in angle, has a larger bearing angle than the obstacle. See, these two have flipped here. And you're still sitting in this attractor. You know, the sum is again the green line, still this attractor. You see, actually, the alternative has almost disappeared. It's just bifurcating here. So a tangent bifurcation is going to be gone in a moment, meaning that at this point you can barely still turn on the spot and go the other way. Maybe intuitive. A moment later, that only one solution left, maybe to go around the obstacle on the left, which is what this attractor drives. Yeah. So the answer to the original question, how you can have complex behavior even though you're sitting in an attractor, is that the attractor actually moves when you're moving around, because the attractor reflects these constraints from bearings of objects, and these constraints depend on where you are in the plane, and as you're moving, that changes. So what you actually have to do is move sufficiently slowly so that the dynamics can relax. That is the dynamical variable heading the plan, can go to the attractor and follow the attractor as the attractor moves. It will be, the attractor shifts a little bit, it will have to change heading, and that mathematically speaking takes some time, exponential relaxation, and you need to make sure that you stay close enough to the attractors to inherit the properties of the attractor to fulfill the constraints. This is an extra constraint on some of the very simple vehicles that we've built this on, like we did this with a so-called Lego robot at some point, which is very, very minimal. And I'll give you a lecture about that. It's a slightly different approach, actually, a very interesting variant. And with that 8-bit controller on that robot, it was a real bottleneck because the dynamical system, you know that from last week, is solved numerically on the robot, has a certain discretization step. We use the Euler procedure. And because of that, we can only compute this fast. It's actually a real sensor bottleneck is the sensors, which I haven't talked about. They take some time to acquire the sensor information. So it takes a minimal amount of time to make one computational step. That will be your Euler step. And then you can sort of estimate, well, I can take a relaxation time of that dynamic. So this slope determines how quickly you relax. That has to be larger than that Euler step. Let's say we said 5 is 5 times the Euler step. That's sort of the fastest time scale you could possibly realize with that dynamics. So if you have an Euler step, let's say of 1 millisecond, then you have to have a relaxation time of 5 milliseconds. And then you then can kind of estimate, then you can determine from that how fast you could drive so that your attractor moves at a rate that you can still track. For instance, you can theoretically determine that the attractor will be moving most strongly if some target or obstacles on the right is off to the side, 90 degrees to your current path. And in that limited case, you can figure out, how fast you can drive. And so in actually some of the robots, we had to drive somewhat slowly just because of that, because the computer was so bad that it couldn't compute faster. If we did this now with a more powerful computer on board, then we could actually drive arbitrarily fast. I mean, arbitrarily in practical terms of like the sensors themselves need some time often to estimate distance, and there's a limit there. Not computational limit. Yeah. So you're actually tracking moving attractors, but the analysis is just always instantaneous about attraction, and you have to make sure that that limit case is fulfilled. So this is a example. This is 30 years or how long ago? 30 years ago. It was considered a good robot platform. Then it actually sucked, and this was a huge computer we used for some form of image analysis. So we determined obstacles and object targets and so on from image analysis. We had a stereo camera system that were extracting distances, and they were extracting any information that deviates from the plane. Those were obstacles, a lot of overhead for that. And we would then be planning passes of pretty fat vehicles, so couldn't make a very complex landscape for that. This was at Ruhr University in the building ND, which is biology in there. We had a big empty space there, which is now built up, unfortunately. So this when I first worked in Bochum before I went to France a long time ago. So here's an example of the kind of things they would do. These are these individual little measurements. So So we see that you don't have obstacles as a object. You have just some readings of stuff that you want to avoid. And you have some problems of how to integrate, would each of those make a contribution? We made a whole theoretical analysis of that. And I don't want to, I'll go a little bit into that next week. So that's just one example of us really bringing about such motion in a robot. It was not done so extensively because you need a lot of space to do quantitative work with a big robot like that. And we did much more with smaller robots later in France. Good. So I already referred to this as a symbolic approach, and that's sort of the manner of speaking, because we're talking about objects, obstacles and targets as objects, like identity. Then I've moved, and then there's another input at this angle that comes from this obstacle. And of course, on the one hand, to get that kind of information from the world is actually demanding. You have to have a perceptual system that can really track objects over time. And most important problem is here segmenting it. So knowing which readings belong to the same object, so that you would, let's say, group all of those into one repulsion. Or should I take that as a separate one? That would be a question. Is this just one object? So that's generally demanding. It's actually not really necessary, because you don't care whether it's an object. For obstacles, you don't care if it's an object or not. You just care that you don't collide with whatever there is. So even if there were individual objects at each of these measurement locations, you wouldn't want to drive, for instance, through those, because the vehicle is too fat to fit through there. So a subsymbolic approach where we just take sensor readings would be appropriate. And that's what we developed next, which happened to be when I was in Marseille, and I'll explain that to you next week. And that actually has an interesting relationship to biology, to some ways. Animals do this stuff. Now, what I want to do today, though, is show to you a experiment that some colleagues at Brown University in Providence, Rhode Island in US did. It was inspired by this work. I visited this lab, which I knew from my past in psychology, modeling human movement and actual perception patterns. And they just had built a cave, virtual reality system, a pretty large one, which at the time, this was published in 2003. I think this started in maybe 99 or something. I don't remember exactly. And so now you have these systems all over the place. This was still very new at the time. So they had a large room in which people could walk around, and you could show them scenes that they will be seeing in their head-mounted display in that room. And that gave these researchers the possibility to manipulate precisely the metrics of the layout, right? You could just in the real world, but you would have to put a target, an obstacle, and you can't really control when people see the obstacle or what their initial angle is and so on. Doing this in virtual reality gave them the chance, and maybe a little bit overkill, but that's how it was done. Give them a chance to manipulate precisely when an obstacle is visible, at which angle, and so on. I'll show you a couple of examples. So this is an appropriate model case of this symbolic approach, because humans do actually have that perception. So they really see in the virtual reality, these were just some cylinder kind of objects. But people do, of course, segment the world into objects and avoid objects. And in fact, there is some evidence from, not from locomotion, but from arm movement, that people really think of an object as a whole. And sometimes they do have trouble, like would collide with maybe a corner of the objects, because the center there avoidance sort of on the center of the object. And so if the object has some something sticks out from it, then you're more likely to collide with that. And you might actually have experienced that when you avoid obstacles in reaching, you don't do that perfectly. Sometimes you do collide, right? I do that all the time in the kitchen. So many of my glasses are broken because I hit something with a glass, and the glass falls out of my hand. We don't do that perfectly. Now in whole body locomotion, it's a much simpler case, of course, it's just in the plane. So here, I'll take you through two experiments, very simple experiments. So what they did is they had participants start somewhere, begin to walk, Well, in the virtual reality, they see it's homogeneous to the surface. And then you can control that, for instance, after walking 1 meter, a goal appears. The goal is encoded by, I have a question here, encoded by the color. Somebody is actually pointing to stuff like that. It's good. Yeah. So these days, you probably do these experiments now. You have to have a large area, so because you're not seeing the real world, it has to be large without obstacles, so you can walk without danger. So that's you know, a real practical constraint with virtual reality systems. If you're in your little student apartment and have only 2 meters free to walk, then you have trouble with the virtual world. And so here they controlled walking by making this target appear at a controlled distance and a controlled time in walking and a controlled angle. So for instance, after they've set them up to walk, the goal appears at a variety of different angles from that current walking direction and at a variety of distances from the participant. And then you essentially see how they move to the target, how they turn. And here are some examples of that. So here is the example where the target appears at 4 meters distance from you, and the different traces are different initial values of the initial angles from the target. So the target appears at minus 25, 20 to minus 5, and here on the other side 25 to 5 degrees. What is plotted is the rate of change, the turning rate of these individuals, as a function of the deviation from the direction to the target. So all the angles are shifted so that it's centered on the target, where the target appears. They call it goal here. You can see roughly that there is this dynamics that we expect, right? There's phi dot versus phi has this zero crossing at the goal and has a negative slope. That's what we want. What's a little odd is that you have different curves, because if it was this equation that we want, then there would be, for your initial heading, there would be one curve, right? And so you see their initial curves a little different, and we'll get to that. While the other manipulation where you just take one initial angle at which the target appears and you vary the distance, you could think of those as being different samples of the kind of curve we're postulating. Let's say, for instance, the target appears very close to you, then it will be this curve on the left going over into this curve on the right, and that it really has the right shape. And that will be, you know, have an attractor here. And then as the distance increases, the steepness of this function is smaller. It makes sense that if it's close, you have to turn hard, so you have a high turning rate. If it's further away, it turns more slowly. So this way you could guess the dependence of the slope of that curve that determines the amplitude as a function of distance. And large distance would be less steep. And then the second experiment was where they do the same thing. In this case, actually, there is a goal from the start in 10 meters distance. And I think in this data, the goal is actually always in the direction of your initial heading. And as you're walking after 1 meter, an obstacle appears again in different angular distances from your current heading and different distances. And this is what you observe. I think they only did it on one side, I don't remember, or maybe this is symmetrically put on the same side. So again, this would be now the angle plotted centered in the obstacle. So the obstacle would be here. And you have, again, at the 4 meter condition, the different angular orientations. And you see that there is turning away. So a positive turning rate, turning away from the obstacle. So the positive slope, if you think of this function we're talking about, there will be this positive slope function that then falls off. You can see that there's they essentially not deviating somewhere here. Now they overshoot, also interesting. So they're not perfectly, leaving the obstacle behind when they are, after having turned enough, overshoot that avoidance. Again, these different curves should really lie on top of each other, because when you're starting with 8, you should be just going to this curve with 8, and it's not actually exactly true. We'll look at that. The distance dependent, of course, is not predicted by the dynamics, so that's empirical. And you see they all have the same shape. And when the obstacle is very close, you turn more sharply. That also makes sense. Suddenly an obstacle appears, you have to turn sharply. So something qualitative about this fits, but there are some differences. So they use the same notation as we do. They call this, by the way, I put this paper on the webpage, so you can have a look at this. It's only for registered readers because I don't own the copyright to that paper. So this would be the angle to the goal, and the psi naught is actually O, psi O for obstacle, and phi is the heading direction. And so, as I was already hinting, the first order dynamics that we have isn't quite right, because these, for a given initial distance, angular distance, you have different values depending on where you started. So that isn't quite right. And the answer to that is you need a second order equation. You need two variables that also keep track of the initial heading. And so they added essentially just a higher derivative with a damping term, and everything else is essentially the dynamics that we have. And I'll explain to you in a moment how that works. So here is the attraction to the goal. That will be a linear function. It should be actually a sine and cosine function, but they only looked at it locally, so it didn't matter the deviation from sine and cosine. And this is sort of the dependence on distance. So they had a parameter that controlled how strong you fall off with distance, and a constant. So even at large distance, there's some remaining attraction effect. And so they fitted these parameters. So you have C1, the fall off with distance. That's, I think, here, the fall off with distance, and this plateau value that you have at large distance. And there's a prefactor here that is sort of prefactor between the scaling. And then the obstacle avoidance has a positive slope here around psi, also just a linear function. And then a range limiting term. We use the Gaussian, they use this absolute value. It's a little bit ugly, but no, does its job. These two terms multiplied with each other here create this repulsive force sledge, sort of like I intuited. And the distance dependence is, again, assumed exponential. That is, another parameter tells you over which time distance scale does this prefactor decay in the initial scale for the smallest distances is another parameter. So I have a handful of parameters to fit, and can fit that all these curves. I want to first, let me just show you if it fits that you can find parameter values where these different conditions are well captured, quite well. And they have more data than this example, so it's a good model. Why does it work? I actually gave you a second task on the exercise sheet to figure that out. So to connect that to the model. So one way to see that immediately, that this is consistent with the dynamics that we had, is to say, well, what they did is really add an inertial term, right? If you go to second order, that means that you can't turn instantaneously. You have to have it takes some time to ramp up velocity up or down. That would be the account for why the initial heading matters. That is, these people have inertia, and they physically have inertia. So one would say they're planning their movement intentions, take that into account, or it's even caused by the physics. We don't really know. And so one way, so if you think of this inertia, you can say, well, if I'm neglecting the inertia, that would mean the prefactor here, which is normalized away, would be z to 0. That would be 0 inertia. And if this was a Newtonian equation, then the thing here in front of that would be the inertial moment. If it was linear, it would be mass. If it's angular, it would be the inertial moment. And that determines the inertia. So if you make that 0, then you would have a 0 here, and you put this phi dot on the other side, then you have, forget the b, you would have phi dot equals, and then you have on the right-hand side exactly the dynamics that we're using. I mean, except for the functional form, but qualitatively the dynamics that I just presented to you from the robotics examples. So you can see that in the limit of small inertia, you recover the model that we had. On the exercise sheet, I'm inviting you to do a more rigorous analysis by computing the fixed points and their stability of this second order dynamics. And then to see if they really have the correct property. I think I'm asking you to do that only for the attractor part, but you could do the same for the repeller part. It's just opposite sign, right? I don't remember. Maybe I even ask you just for the repeller part. So I'm just asking you to do that for one of these two to make it simple. So this is just a slight generalization of the dynamics that we had that deals with this inertia. So it captures quite well how humans walk, and then they can do funny things like, here's another example of how it matches. They can look at cases. So I find that most interesting when there are targets here in different positions and obstacle here in front. And then you can see that there would be maybe some targets where you'd want to go around on the right and other cases where you go around on the left. And they did have conditions like that in experiments. So they had also some conditions that were like this. And they observed then apparently different individuals or in different runs, people would choose a different way around the obstacle. And here's the percent try, so the probability of people taking the inside route as a function of the initial, how far the goal is from in angle from the initial heading when after 1 meter walking. And apparently the model can capture that. So depends also on distance. So you see there were some real constraints on the parameters. Now, so a very simple model that captures human locomotor behavior. I mean, the displacement, pedestrian movement, displacement in the plane. And some of you might know that there's a whole industry of these sorts of models in the meantime. This is something that is done actually in Duisburg. Michael Schreckenberg is a physicist, and traffic physics is the name of that field, where people study things like that. There's someone else called Helbing in Zurich does that. And there's a third chair somewhere in Germany. I think it's maybe in Leipzig or somewhere there. I forgot the name of the person. So there are people who do these kind of simulations. They do that for pedestrians, for instance, evacuation plans, simulation of how people would evacuate a building, and you have to have sort of models how people would avoid collision with each other, avoid collision with the walls. You get these kind of insights that people would, there would be blockages when the corridor narrows, and that has real implications for security. It's now a procedure to simulate things like that before you construct buildings. And famously, this in Duisburg was this a parade where people died when panic broke out. I forgot the name of that kind of parade, but many of you will know that. And Michael Schreckenberg actually got a little bit into trouble because he had apparently simulated and said it was okay. Now, it's not perfect. Some parameters might have been off, or he was too gave in to the pressure to come up with a positive solution. I don't know. And actually, this person in Zurich, Helbing, has written an analysis of what went wrong in the meantime. The models used in these kind of simulations, when you have hundreds of little data points where you simulate humans, are not as detailed as this. This would be called a micro model, because you're modeling the individual's behavior as a function really of heading directions on. You can see there could be other parameters like how fast you walk, and maybe some kind of aggressiveness, essentially how strong your repulsion term is compared to a term where you try to achieve a certain desired forward speed. So other parameters that are not controlled in this experiment. While these models that are similar like that are more like models that are sort of fluid dynamical models where the human is a point, and certain forces act on that point in terms of some diffusion. And so they tend to have similar speed to their neighbors, and then walls create some friction and so on. So there are different levels of description for that. There's a whole industry, again, like that. Another aspect of that is actually modeling cars and driving behavior. And I actually dabbled a little bit in that and made the only real kinematic model of lane change behavior. With similar techniques, and I don't go into that. I don't do this anymore because it's a field of its own. So many people working in that field. I couldn't do that on the side. So kind of interesting. So it's even somewhat applied, but I'm just doing this sort of to teach the concept. So we've developed these ideas much more in the direction of more complex robotics of reaching, and I will get to that in the second part of the course. Okay, that would be this first lecture, and I'll switch back.